let's talk about the best study ever written. From this study, we learned that chocolate increases weight loss. That's right, eat chocolate and lose weight. Okay, well, before we get too excited, let's make sure this comes from a valid source. This study was done by Johannes Bohannan from the Institute of Diet and Health. Sounds legit. And it was posted in the International Archives of Medicine. That too sounds promising. The study methodology divided people in 3 groups. One group ate low carb, one group ate low carb and ate chocolate, and a third group, called a control, ate an unrestricted diet. They then measured many characteristics on these people, including their weight. Here's a chart showing the daily weight loss by group. It really looks incredible. Look at their conclusion. Chocolate caused weight loss turbo. Now, look at this table of numbers. Isn't it also convincing? Wait, what does it say at the bottom? Does it say there were only 5 people in the chocolate eating condition and 4 in the low carb only group? Wow, that's a really small number of people. Should we be skeptical of the results because of that? Well, after this study came out, all of these news sites and magazines shared the results of the study. That means it must be okay, right? Well, that is what everybody assumed until this headline came out. This follow-up article was written by the lead author on the chocolate study. It turns out he purposely designed the worst study possible. He gave himself false credentials. While he really does have a PhD, he doesn't work at the Institute of Diet and Health because it doesn't exist. And he paid to get his study published in a journal. Why? Well, his point was this: people, those in research and journalism and everybody else, need to think more critically about the design of an experiment before sharing the results. He feels we need to pay attention to bad studies and call them out rather than amplifying them. So, what makes a study good or bad? First, let's talk about sampling. When we do research, we want to make a statement about a population. So what is a population? Well, it's everyone. If we wanted to know if a new drug is effective for adults who get headaches, then the population is every adult who gets a headache ever. We know that it's impossible to get all of those people to take our drug in order to determine if it's effective. So instead, we rely on samples. Samples are when we take a representative subset or part of the population. When we do a drug trial, we get a sample of people, a smaller group than the total population, and we have them take the drug. Once we take a sample, we can use that data in 2 ways. First, we can calculate descriptive statistics on it. These are statistics that just explain what we see in the sample. What patterns and trends are there? We can also calculate inferential statistics, and this is the heart of what we do as statisticians. This is where we can use a properly gathered sample with well-collected data to make an inference about the population. What is an inference? Well, it's essentially a well-rationed, science-based, educated guess about the population. What does that mean? Well, if we did everything right, the population should look like what we got from the sample. If the drug works for the sample, then it should work for the population as well. But sometimes things can go wrong. There are 2 primary types of error: sampling error and bias. Sampling error is the inherent variation in statistics. It happens by chance. But we can also have a biased sample, or one that is not representative of the population. Sampling error means that every time we do a study with a new sample, we'll get slightly different results. Hopefully, though, these results come back fairly similarly with minor differences. Look at the difference here between the target on the right and on the left. On the left, each study marked by a dot has slightly different results. This is normal and to be expected. But on the right, each study is wildly different, and that's a real problem. The other error we can have is bias. Now, a good study has a sample that represents the population. They should be similar in important characteristics like age, gender, health status, to make a solid inference. An example of a bias sample would be, say, I want to estimate the average height of students on your campus. So I took a sample that consisted only of your basketball teams. Then I inferred that that average could tell me the average height of all students on campus. Do you think that would be accurate? No way, because I took a biased sample. Using that same target example, again, you can see on the bottom, bias means that we are consistently off target from where the population bullseye really is. The final thing we must watch for in studies are confounding or lurking variables. A lurking variable is one that has an effect on the relationship between your variables, but wasn't one of the variables you intended to study. Think about this chart of damage caused by fires versus the number of firefighters who responded to a fire call. Clearly, it implies we should limit the number of firefighters that respond to fires because they cause so much money and damage. But is there a lurking variable here? Of course there is. It's the intensity of the fire. An intense fire causes both more firefighters to respond and more damage to be done. So being aware of lurking variables that could arise in a study is also crucial. Designing an effective study takes time and energy, but if we don't take the precautions, we cannot assume the results of the study are valid or useful. So what does all of this mean? Don't eat chocolate thinking it will make you lose weight.